Hi there, this is SS Tripathi welcoming all of you to my next video on reaction stoichiometry part 1. In the previous video we had seen the composition stoichiometry. Today we shall take up the reaction stoichiometry. If you have not yet subscribed to my channel, please do so. If you like that all my videos will be informed to you, and also if you like a particular video, do not hesitate to press the like button. 11th lecture on BCC, basic concepts in chemistry, and in the last video, in the last program, we discussed about composition stoichiometry, and today we shall be taking reaction stoichiometry. We already know the difference between the two, where in composition we are simply to find out the mass ratio of elements from the molecular formula or from the mass percentage data. We find the empirical formula and then molecular formula. You all know that. But here we have to deal with a reaction, and as I have already told you, the steps required. Let me read out these things we already have discussed in our previous video. The balanced chemical equation gives the reaction stoichiometry. It gives a quantitative relationship between reactant-reactant, reactant-product, and product-product. Often one reactant is taken in large excess than the other. The other reactant, which is taken in lesser amount, is called the limiting reactant. I repeat, limiting reactant we sometimes abbreviate as LR. Which is all consumed during a reaction, and we presume in most of the calculations that the reaction is complete. The reaction is complete. The reaction is complete means the limiting reactant is totally exhausted. Nothing is left out. Obviously, some amount of the other reactant taken in excess will be left out, but the limiting reactant will be all consumed. That is our assumption while solving a stoichiometric problem, right? But in some cases, you will be given the actual yield that a particular person, student, has performed the same reaction, and the student has got this much of amount, product amount, but the prediction from the equation for the completion of the reaction, that prediction says something else, higher amount, but the fellow has got a lower amount of the product. That happens in laboratory conditions. Usually we don't get the amount of product equal to that predicted by stoichiometric calculations, by the assumption that the limiting reactant is completely exhausted, right? In that case, you will be asked to give the percentage yield. And how to find the percentage yield? This is the percentage yield in a reaction is the actual amount formed, actual mass of the product formed, divided by the theoretical yield. This L has been separated. Let us unite them. Let us unite them. Divided by the theoretical yield from the stoichiometric calculation into 100. In very, very rare situations, you will be asked to give the percentage yield in a reaction. Percentage yield means the actual amount of product formed divided by the theoretical amount of product that would have been formed if the reaction would have been complete into 100. From the amount of product formed, the amount of reactant consumed and the amount of other product formed can be calculated from the balanced equation. And that is what is reaction stoichiometry. Write the balanced equation, write the equation, balance it perfectly well, and then establish a relationship between reactant-reactant, reactant-product, product-product, and whatnot. Just looking to the balanced equation. That is nothing but the reaction stoichiometry. Now, in the actual experiment, how much of the product is formed? From that, you can find out the amount of reactant consumed, and also you can find out what is the amount of product formed when reactant amount is given, or what is the amount of the other reactant consumed when one reactant data is given. So whatever is given and whatever will be asked, that all can be dealt with in while writing the balanced chemical equation. So reaction stoichiometry is therefore called quantitative analysis. Quantitative analysis, amounts. It may be in terms of moles, it may be in terms of mass, or if it is a gas, it can be in terms of the gaseous volume. And these are the 5 steps that you have to adhere to. Number 1, predict the reaction correctly with proper logic. And most of the problems, numerical problems, you will not be given the entire equation. You have to predict. And in some problems you are given ready-made. And in some cases, the balanced equation, just to eat, it's a made dish or a cake that you will straight away eat. But in most others, you will be forced to predict what will be the products and also to balance. That is a must. Then balance it correctly. For redox equations, you have to apply some convincing method like ON method. You can't apply the heat and trial method, which is actually not recommended for a bit complicated redox reaction equation, in which you have to look for the total number of electrons lost should be equal to the total number of electrons gained. Then write the molar masses or molar volumes below each species which are involved in the calculation in the balanced equation. Multiply the coefficients in the balanced equation with the molar masses or molar volumes, because we have to first find out the stoichiometry molar on molar basis. Supposing 2A plus 3B gives C plus 4D. So 2A, 2 into A, the molar mass of A or the molar volume of A. If you are given volume data, then molar volume 22.4 liters at STP. If mass data, into its molar mass. If only moles, so nothing has to be written, only the coefficient 2 or 3, 2 in this case 2. Similarly, 3B, 3 into its molar mass or 3 into its molar volume, 22.4 liters, or simply 3 moles. That's it. And in the right side, you have to also do similar things. Use the data given for any species. In the numerical, you will be given the data for a particular species, may it be a reactant or product. You use that data looking to the stoichiometry which you have written. You can find out by unitary method what will be the amount produced if this amount of reactant has reacted, or what will be the amount of the reactant required to produce this amount of the product. The actual amount of product, if it is given in any numerical, hardly you will find a problem. You will be given the actual amount of product formed. Most of the cases you will be asked what is the amount of product formed. Means 100% reaction is complete. The limiting reactant is all exhausted. Now these stoichiometry, reaction stoichiometry, can be otherwise called quantitative analysis. And whatever we are going to do here in this program is simple stoichiometry. Nothing to do with solution, aqueous solution. We will be not using any solution having any strength like molarity, normality. That we won't be using in this program. We will be analyzing everything in terms of mass, mole, and volume. If it is a gas, it is volume, right? So, and it is sometimes called gravimetric analysis, particularly when the substance to be analyzed is a mixture containing several entities, several species. That is called the analyte, and we are analyzing through measurement of mass. In that case, it is called gravimetric analysis. So, but not all stoichiometries will be called gravimetric analysis. If you are analyzing a sample, mixture of A, B, C, and you are, performing an experiment, A and B, they give different reactions. And you measure the amount of the product formed, the dry product formed, and then establish a correlationship on the basis of mass. Then we call it gravimetric analysis. And if it involves a solution, involve a titration experiment, which I'll be doing in our next program in this BCC, then that is called volumetric analysis. So here we'll not be doing volumetric analysis. We'll be just using their amounts, their direct amounts, either in moles or in mass or in volumes, that is gaseous volumes, right? Now these are the things we are going to cover in this lecture, a few, and in the second lecture the remaining. Mole, mass, volume, mole, mass, volume, then volume. That is the volume analysis, right? Now, so far you already have a clear knowledge about percentage composition. Either it will be mass percentage or mole percentage. And they should not be confused with one another. Mass percentage and mole percentage are never the same if the elements are different, So mostly the data given is mass percent. That is the mass of a single component divided by the mass of the mixture into 100. That is the mass percentage of a particular component. But if it is a mole percentage by mole, then there is the number of moles of one species by total number of moles into 100. You already know how to find the mole fraction. Mole fraction into 100 becomes mole percent. Now, I am going to caution you these things. I am sorry, here I have written in a vernacular language sometime, so I am trying to remove it. Otherwise, if you are a participant or a viewer not knowing this language, you will be feeling really very weird. So I have rubbed off that language, that is Odia language. I hail from this Odisha, where the native language is Odia. You can search, Google search, anywhere you are in the world, you can Google search. Odia is a honored language in the world community. You will find in the list of languages, you will find Odia is one, right? And as you guys are proud of your language, mother tongue, we are also equally proud of our language, native language. But at the same time, I have no hesitation to concede that English is the international language of communication, and perhaps nature has evolved in such a wonderful manner that the English people have, for their empire, they had established their kingdoms throughout the world almost, Perhaps the nature wanted that there will be a globalization of mankind by a single language, and that single language is the language of English. So beautiful, so easy, and everybody likes the language, right? So you must distinguish clearly between the two volumes. One is the gaseous volume. If it is a pure gas or gaseous mixture and you are given some liters, some milliliters, it is a gaseous volume. And in that gram molar volume, 22.4 liters is a huge important data. But if you are given a solution volume, aqueous solution volume, then in some students, they confuse. They are given 22, supposing by a deliberate attempt, the examiner gives you 22.4 ml of a sulfuric acid solution. Since it's given 22.4, you will be confused to use the data 22.4 liters, 1 mole. It's not that. A gas 22.4 liters is 1 mole at NTP 22.4 liters. But not liquids, not solids, not liquids. Therefore, whenever you are looking to any volume data, this much ml, this much EMQ, this much liters, this much meter cube, first make sure that you are handling gaseous volume. If so, then 22.4 will be used. If not, then you will be looking for the density of the solution and all that. That will be doing in our next programs, solutions to stoichiometry. Now, let us have some discussion about the mole volume, mass volume, and all that. Mole. I have just given one numerical to explain to you how easy these stoichiometric calculations are. How many moles? How many moles of pure and dry barium phosphate will be formed when 0.2 mole of pure barium nitrate will react with excess sodium phosphate in aqueous solution? Which is the limiting reactant here? Also calculate the number of moles of pure sodium phosphate consumed during the reaction, right? Now, our first job is to write the equation, correct formula. Unless you write correct formula, you can't balance. So barium nitrate reacts with sodium phosphate to give you barium phosphate and sodium nitrate. And I have balanced it. 3 here, so 3 here. Nitrate will be 6, so 6 here. This will be 2. So everything is balanced. Now, obviously, the limiting reactant is barium nitrate because the question is saying that sodium phosphate is taken in excess. I told you that in almost all stoichiometric problems, you have to take one reactant excess, so that the limiting reactant, the one which is present in smaller amount, that will be exhausted. And all calculation will be based on that limiting reactant. And the mass or the amount of the excess reactant is not given unless it is a numerical based on limiting reactant, where both the data, the amounts of both the reactants are given in a numerical. But you know that if only one data is given, you can find out the other data, mass amounts from only one data. So if 2 data are given, definitely you'll be suspecting the bona fides. I mean that means one of them has to be limiting, the other one has to be excess, and we have to take the limiting reactant to find out the product amount, not the excess reactant, because not all of that reactant has been consumed. A part has been left out, so you can't use the data to find out the amount of product. So in these problems that we'll be doing in this lecture, you will be knowing which one is excess, because the question will be telling clearly that sodium phosphate is an excess. And also he is asking how much of sodium phosphate will be required in this reaction. Now we write the stoichiometry. This is called the stoichiometry relationship, right? This first line, I suggest you, whenever we are performing in the stoichiometric calculation, then leave a space below the equation. Leave a space. All calculations have to be done below the equation, because to waste time to write down in a language manner and wasting time is almost a futile exercise, wasting of time. So the relationship, this is the stoichiometric relationship. Stoichio. 3 moles will react with 2 moles to produce 1 mole of barium phosphate and 6 moles of sodium nitrate. This is mole-mole relationship. We are not interested to find the mass. So why to write the mass, molar mass? So 3 here, 2 here, 1 here, and 6 here. Then let's see what the question is demanding from us. The data is barium nitrate pure, because all these data given, this data is given is a pure substance, but we have to perform the experiment in aqueous solution. So whenever we get a precipitate of barium phosphate, we have to filter it out, dry it, and take the mass of the dried sodium phosphate till constant mass, because some moisture will be there. So if supposing somebody asked to perform the experiment, not merely calculate in a pen and paper, that is called stoichiometry. Stoichiometric calculation is a calculation in the pen and paper to find out how much of things will be required or produced if the reaction is complete, which means the limiting reactant is completely exhausted out. So if 3 moles consume 2 moles and produce 1 mole, sodium nitrate is not asking about it. I have written, but the question is not demanding to find the number of moles of sodium nitrate. So you may not write. You write only this 2, 3, 2, 1. And if 3, 2, 1 is the stoichiometric relationship, then what is 0.2 against what? So 3 gives 2, 3 requires 2, then 1 will require 2 by 3, and 0.2 into 0.2, that is coming 0.133 mole of sodium phosphate will be consumed. Similarly, if 3 moles give 1 mole of the product barium phosphate, then 0.2 mole will be giving 1 by 3 into 0.2, that is 0.0667 mole, right? So in one line, if you are little intelligent, there is no point to waste time in calculating, separately, one for product, one for the other reactant. So everything to be done below the question, the balanced equation. Therefore, you leave a sizable space empty before you go to the next sum or next data or next equation. You leave some space for stoichiometric calculation. Now some students, they are not the same thing. Some students, they are not confident to perform in one line. 3 mole, 2 mole, 1 mole, 0.2 mole, how many moles? So I suggest them to go for a step-by-step analysis. 3 moles of barium nitrate, write down, or if you will not write, you just indicate 3 moles of barium nitrate requires 2 moles of sodium phosphate. You also write down requires also. Then how much 0.2 mole of barium nitrate will be requiring how much? 2 by 3 into 0.2, right? And then again write down separately 3 moles of barium nitrate produces 1 mole of barium phosphate. Then 0.2 mole of barium nitrate will produce how many moles of barium phosphate? You do it separately so that you know, these things, the confusion might not arise at all. Now this is the next relationship, that is mole mass. You will be given the data of one of the species, maybe reactant, maybe product, in mass, gram or kg, and the other one in mole. See this example. How many moles? Here the reactant amount is not known, and this amount will be expressed in terms of moles. How many moles of potassium chlorate on strong heating will produce 8 gram of oxygen gas? So the product amount is given, but the reactant mole is asked. So why to waste time? Whichever species the mole data is given or asked, you write the coefficient 2 mole. Don't convert it into mass. Don't write 2 into the molar mass. That will be in gram, but we are not interested in gram. We are interested in mole. So 2 moles produces 3 moles here, since the mass of oxygen is given in gram. So 3 into gram molar mass, 3 into 32, right? So 2 moles of potassium chlorate, here mole, here mass. 3 mole means this. This is the stoichiometry, but the actual experiment is not in terms of molar. 3 moles has not been produced. Had it been 3 moles, this would have been 96. 3 2s are 6, 3 3s are 9, 96 moles. 96 grams. But the data is only 8 grams. So we have to make a unitary method if this is produced by. Now we will be doing calculation in the left. This is a leftward calculation. So I'm sure since you are in class 11, you will understand that this much is produced by this many moles of KClO3. Then 1 gram will be produced by 2 by 3 into 32, and 8 gram will be produced by 2 by 3 into 32 into 8, and when we simplify, you get 0.1667 mole, right? So we are calculating in the left side because the right data is given, but truly you know, in lower level student, they are said that whatever data is given, that should be kept in the left. I mean, their stoichiometry should be kept in the left, so that by unitary method you can find out what is the mass of the mole of the product formed from, or what is the molar mass of the reactant used to produce these many mass or these many moles of the product. For example, here I would suggest beginners, if you are not very confident to grasp what I have saying here, calculation at the left, it is always recommended that you start writing in language. This is a passive voice because the amount of product is given, data is given, and the amount of the reactant is asked. Therefore, this should be kept in right, this should be kept in left. So left, 3 into 32 grams of oxygen is produced by 2 moles of KClO3. So 8 gram of oxygen is produced by how many moles of KClO3? It's coming 1.6, right? Same thing as 0.1667. Now let us have another problem, that is mass. Both the species are in terms of gram or kg mass. No mole, only mass. What mass, an example, what mass of residue will be formed by strongly heating 4.2 gram of sodium hydrogen carbonate or sodium bicarbonate till constant mass is obtained? I suggest, if you have taken my LOC course perfectly well, then there will be no reason why you cannot write the equation correctly and balance them. If not, you will be facing difficulties here in BCC. So I will suggest to first go through that LOC, particularly the balancing part, I mean prediction part, so that you can not only correctly predict but also can correctly balance the equation. So here sodium bicarbonate on heating will produce, the residue is sodium carbonate, not oxide. Sodium carbonate, carbon dioxide and water. This much you have to know, that you have to complete LOC course. Otherwise you will definitely seeking the help of someone to get you the equation. You may balance it. If it is a simple reaction, equation can be balanced by heat and trial method. So just by multiplying 2 here, it is balanced. 2 sodium bicarbonate gives sodium carbonate plus carbon dioxide plus water. Now since the reactant data is given, so we have a rightward calculation. If the product data is given, we have a leftward calculation, right? In a shortcut method. Now 2 into, since mass-mass relationship is to be established, so the molar mass of sodium bicarbonate is 84. That is 23 plus 1 plus carbon is 12 and 16 3s are 48, totals 84. So 2 molar mass, 2 gram molar mass, 2 into 84 grams produces 1 mole, that is 106 gram is the molar mass, gram molar mass of sodium carbonate. 23 into 2 plus 12 plus 16 3s are 48, it will be 106. So if this much gives this much, then 4.2 gram will give how much? This by this into this, so will give you 2.65 gram of the residue. In fact, carbon dioxide and moisture, water vapor, will go up on heating. So the only residue that will be left out is sodium carbonate, right? So I have already done that. Now let us take up an example of mole volume relationship, where you are given the data of one species either in terms of volume or mole, and you are asked the other species either in terms of volume or mole. Let's see this example. How many moles of manganese 4 oxide by reacting with excess concentrated HCl will produce 5.6 liters of chlorine gas at STP? Let us read again. How many moles of manganese 4 oxide or manganese dioxide by reacting with excess conc HCl, where excess means this is the limiting reactant, this is the excess reactant. So the data of the limiting reactant is given, not the excess reactant. But if both the data are given, then definitely we will have an element of suspicion as to assess which one out of the 2 is limiting, and that one we will be using for solving, finding out the product amount and also the other reactant which has been consumed, right, which has been taken in excess, and the data given, right? Now this, after writing the equation, chlorine is one of the products. Obviously manganese from +4 it comes to +2, and chlorine goes from -1 to 0. This is a redox reaction, and hence we balanced it 4 and 2 here. So the data, the product data is given 5.6 liters, but we have to establish the stoichiometry first. I told you, stoichiometric first. That means 1 mole, instead of writing 71 grams or 1 mole, we write 1 molar volume. What is 1 molar volume at STP? It's 22.4 liters. So below chlorine you write, since it is 1 mole, the volume of 1 mole is 22.4 liters, and below manganese dioxide you write 1 mole, simply 1 mole, because you are asked to find the number of moles. Why to find mass as a foolish person, if we first find the mass, then convert to mole, will be the most foolish person on earth. So, according to the data given, we have to act in the appropriate way. Here volume, here mole. If 22.4 mole is produced, this is a leftward calculation. I say leftward and rightward. A rightward calculation is normal. Normally it is written also in a subjective explanation. Also we written the same. But the leftward calculation is not mathematically recommended. But we save time by doing a leftward calculation. If 22.4 liters is produced by 1 mole of MnO2, so 5.6 liters will be produced by 1 by 22.4 into 5.6. It is 1 by 4.25 mole of manganese 4 oxide or manganese dioxide. Now, if you are not comfortable, you can do it in this method. Write in language, passive voice, 22.4 liters of chlorine is produced by 1 mole of manganese dioxide. So 5.6 liters will be produced by 0.25 mole of MnO2. So in whichever manner, whichever suits you to your level of reception, you solve with that in that manner, right? Then mass volume. We completed mole volume, say mass volume. What volume of carbon dioxide will be obtained at STP if 10 gram of a sample of anhydrous sodium carbonate, which is 90% pure, reacts with excess dilute HCl. Here again, HCl is the excess reactant. Obviously, sodium carbonate is the limiting reactant. So far, we have not got any example where the data for both the reactants are given. And so far, we have taken one in excess. And the data given is for the limiting reactant. And we will take that data to analyze or to find out the other values. Now what happens here? Which is the limiting reactant here? Obviously sodium carbonate. It's already clearly mentioned it is HCl taken in excess. Also find the mass of pure HCl. Why it is written here? Because you have taken a solution of HCl, an aqueous solution of HCl here, right? But I want to know what is the mass pure HCl consumed during the reaction, because it's not solutions stoichiometry. We have very systematically evolving the topic. Therefore, I have written pure HCl. In later chapter, when I'll discuss volumetric analysis, solutions stoichiometry, there my question will be in a different form. How many milliliters of HCl solution having molarity this and that? So those things are not a subject matter of today's program. Now, write the equation. Sodium carbonate HCl giving you carbon dioxide. Any carbonate with any mineral acid, non-oxidizing mineral acid, you know. This is one of the 11 metathesis reactions that we have discussed in our LOC program. So we have balanced it. Limiting reactant is sodium carbonate, but how much sodium carbonate is really there in the sample? The sample presume that the impurity does not react with HCl. To produce CO2. It may be reacting but will not produce CO2. That means there is no carbonate other than sodium carbonate. Then only we will say that 9 gram is pure sodium carbonate. It is 90% of 10. 90% of 10 gram is the actual pure sodium carbonate. So first we have to find out what is the real mass of sodium carbonate, pure sodium carbonate. This 10 gram is the mass of the impure sample. So 9 gram. So we have to use this 9 gram. If 106 gram, because this is the molecular mass, gram molar mass is 106 gram. is requiring, will be doing in one line. In one go, we shall finish all the three things. If 1 mole means 106 gram is consuming 2 moles, 2 into 36.5 gram to produce 1 mole of gas CO2. 1 mole means 22.4 liters. Why I wrote 22.4 liters? Because it is asking about what volume. What kind of volume is this? I told you there are two types of volumes in stoichiometry. One is the gaseous volume, the other one is the liquid solution volume. Don't confuse one with the other. So here it is a gas, it is a pure gas, no solution. So this volume is gaseous volume. So therefore I wrote 22.4 liters at STP corresponds to 1 mole. Here the coefficient is 1. So if 9 gram is requiring this much, I'm so sorry. If 106 gram is requiring this much and producing 22.4 liters of carbon dioxide, then 9 gram will require how much? 2 into 36.5 divided by 106 into 9. That is coming 6.198 gram. And if 106 gram produces 22.4 liters, then 9 gram will produce 22.4 by 106 into 9. This 1.908 liters. Don't forget to write the units. This is liter, this is gram. But I recommend, if you are not confident to answer in one go below the equation, the balanced equation in 2 lines, then it is better to do step by step. One for one species, the next for the second species, right? Now I have done the same thing here. This same thing here I have done. Separately I have done it here. So 106. No. This is the same repetition. Now this is another problem. It's the same mass volume relationship where you are given the volume of a gas at a different conditions, not STP. This is a non-STP conditions, the volume is given. If that is the case, the first job that we have to do is to convert this volume to STP condition. Then only we shall proceed in our stoichiometric analysis. Let me tell you here that whenever you are having a volume data in a non-STP condition, then your first job is to convert that volume into STP volume, right? But if the volume is asked at a non-STP condition, then your last job is to convert from the STP conditions to the required conditions, to the given conditions, right? So after converting, we found P1 by T1 is equal to P2 by T2. If you do not know this combined gas equation, that is a topic of this BCC, the first lecture on BCC, you just revise that. P1 by T1, P2 by T2. So we got V2 is equal to this. Greatly different from the volume that is given, 239.47 milliliters. The volume, the units will be same. Then stoichiometry. See what is happening. Calcium carbonate on heating obviously will produce calcium oxide. This is the residue, and carbon dioxide will escape into the thin air, right? So here mass, here volume. So 1 mole, the molar mass is 100, 40 plus 12 plus 16 3s are 48. So 100 gram of calcium carbonate produces 1 mole means 22.4 liters or 22,400 milliliters. Because this is in milliliters, it is always better, instead of converting this to liter 0.239, we can convert this to milliliters. So again, this is a leftward calculation. If 22,400 ml at STP of carbon dioxide is produced by 100 gram of calcium carbonate, so these many milliliters at STP will be produced by how much? This divided by this into this, 239.47 ml. So the mass is 1.069 gram. Then that many grams of calcium carbonate will produce on heating 239.47 milliliters of CO2 at STP. But the actual volume was measured under other conditions. You have got this in the calculation, because our interest is to find this, not this. This is already given. So before we go to the next numerical, let me tell you that you handle this volume with caution. Gaseous volume is totally different from a liquid solution volume. We have done this, and this is the last thing in our program. It is 44 minutes, another 15 minutes. What mass of this is successive reaction. That means one reaction, the product of the first reaction will be the reactant in the second reaction. Maybe the product in the second reaction will be the reactant of the third reaction. So these are called successive reactions. And if you are asked to find out the amount of the final product of the final equation, if the reactant amount of the first equation is given, how to find? Obviously, we have to perform 3 calculations, one for every reaction. Each equation has to be balanced. Use the mass of the reactant of the first reaction to find the product, and use this same amount to find out the amount of the product in the second reaction. Again, use the same amount to be used in the third reaction as a reactant to finally find the product, the final product. Let us take a simple case, not a difficult one. It's a very simple one. It goes like this. What mass of potassium chlorate on heating gives just sufficient oxygen gas to completely burn 8 grams of sulfur to sulfur dioxide? Is there any limiting reactant in the second reaction? Is there any limiting reactant in the second reaction? The answer is no, because second reaction, whatever oxygen is produced in the first reaction, all is consumed. This oxygen is required to completely burn 8 grams. That means that oxygen which is produced is exactly sufficient to burn 8 grams of sulfur. So in this case, this is an exact equivalence. That is called exact equivalence. Nothing will be left out. That is very rare. That happens only in theoretically, but practically it rarely happens that you take, if you calculate, first you calculate how much of A is required, and for that amount of A, how much of B is required, and you take these two amounts. Obviously, if they will go for a complete reaction, as we assume for stoichiometric calculation, then you will find no one is limiting, no one is excess. Each one is limiting. Each one is limiting. Both are limiting. Both are consumed completely. Nothing is left out. So, is there any limiting reactant in this second reaction? The answer is no. Also calculate the volume of SO2 formed at STP during the reaction. Now see, you write down, and while you write the first equation, leave a good amount of space for calculation. I funnily say I'd like to share with you, I funnily say to my students that stoichiometric calculation is nothing, calculation below the equation. Calculation below the equation, that's it. All below. So the first reaction is potassium chlorate is heated to produce KCl and O2. Immediately balance this. We have balanced 2, 2, 3. Okay. Then this amount of oxygen which is produced, right, will be exactly combusting, burning 8 grams of sulfur. This is the only data given. You know, since I have already calculated, it might confuse you, but let me tell you, the only data given is this, nothing else. Only data given is 8 grams of sulfur. So what mass of oxygen is required? Tell me which equation or reaction we will tackle first. KClO3 gives oxygen. This oxygen is used to burn sulfur. The mass of sulfur is only given. So we first have to tackle the second to find out how much of oxygen is required. Exactly how much of oxygen is required to combust 8 gram of sulfur. Then stoichiometry. 1 mole, 32 grams, 32 grams. Here the mole means gram atomic mass, here mole means molar mass, molecular mass. So 32 means 8. So 8 gram of oxygen is required in the second reaction. That has come from the first reaction. So this 8 gram. Now let us establish stoichiometry. 2 into the molecular mass. KClO3 has a molecular mass 39 plus 35.5 plus 48, 122.5. So 2 into 122.5. I suggest not to multiply because in many calculations 2, 3, 4 they cancel out. So it is always recommended not to use and not to multiply now. So this will be used during our calculation. Sometimes they will be cancelled out. So 2 into 122.5 gram produces 3 into 32 grams. So since we will go leftwards, 3 into 32 grams of oxygen is produced by this many grams of KClO3. So 8 gram will be produced by how much? This divided by this into 8. This is, I am cautioning once again, this is leftward calculation. You might fail. So better go in language. So if this much of oxygen is produced by this much of KClO3, so 8 gram will be produced by how much? I got 20.416 gram. That is the final answer. What mass of KClO3? So 20.416 gram of KClO3 on heating will produce exactly 8 gram. It will be just sufficient to combust 8 gram of sulfur to sulfur dioxide and calculate the volume of SO2 formed at STP. Now it's very simple. Here I have done before. If the relationship is 32 is producing, 1 mole means 22.4 liters at STP. So if 32 grams of sulfur is producing 22.4 liters of SO2 STP, so 8 gram will produce how much? It will be 22.4 by 32 into 8, so 5.6 liters. So these are very simple problems once you understand. This is another one, and this will be the concluding one. 10 gram of a sample of ammonium sulfate having 80% purity. Again, 10 gram is not the amount to be used. 80% of 10 is to be used. So that is 8 gram. 10 into 80%, that means 80 by 100, 8 gram. So 8 gram of ammonium sulfate was heated with excess of alkali. Maybe NaOH, maybe calcium oxide, whatever. Let us take, for our purpose, because nothing is given which alkali, let us take NaOH. No problem, it will not be required. Is heated with excess of NaOH. This is the excess reactant, this is the limiting reactant to produce ammonia. So all ammonium sulfate gives its equivalent quantity of, ammonia. And that ammonia, all ammonia that was produced was then used to react with excess of copper 2 oxide. Again, the black copper oxide. Excess was taken here because this has to be consumed totally. So the ammonia produced in the first reaction will be allowed to react with hot copper 2 oxide excess to produce metallic copper, nitrogen it is given, copper metal along with nitrogen, and the obvious product is water. Now you balance this equation. Each equation has to be separately balanced. This is balanced, space is left for calculation. This is balanced, space is left for calculation. Right? This is the oxidation number changes from 0 to +2 to 0. So 2 is multiplied here, and here the oxidation number changes from -3 to 0, changes 3. 3 is multiplied here, then heat and trial. I remind you the ON method of balancing equation. Right? So unlike the previous question, for which we started from the second one, here the mass of the first reaction is given, the reactant of the first reaction is given. So we have to first tackle the first equation. If 1 mole, that is molar mass, is 132 gram, you find out nitrogen 2, so 14 2s are 28, then 4 2s are 8, plus sulfur is 32, plus 16 4s are 48. So it's totaling 132 grams of ammonium sulfate is producing 2 into 17 gram. Ammonia is 17 gram of ammonia. So 8 gram of ammonium sulfate will produce how much of ammonia? 2 into 17 by 132 into 8 is coming 2.06 gram. Now we shall be using this amount in the second equation. Now in the second equation, the stoichiometry tells us that 2 into 17 gram produces 3 into 63.5 gram, because copper, the atomic mass is 63.5 gram, and produces 1 mole means 22.4 liters at STP, right? So this is mass volume. One go, in one stroke we calculate all. So if this gives this and this, then 2.06, which is known from the first equation, then 2.06 gram will produce how much of copper? This by this into 2.06, coming 11.4 something gram of copper. And how much liters of nitrogen? 22 by this into 2.06, coming 1.34 liters of nitrogen at STP, right? So now I will tell you another approach to calculate such types of successive reaction problems, numericals. So what I will suggest you to add up all these individual steps and perform some algebraic operations if needed to cancel out those which have been used up. Like in the previous case, ammonia was used up, so cancel ammonia by performing algebraic operation. Or in the first case, oxygen is used up, so cancel them. So there is no point to find out the mass of the product and then use the same in the second reaction. To avoid that, it is always handy to add these two reactions, individually balanced reactions, you have to add up. And if required, some manipulations has to be done here. Fortunately, here to ammonia, they cancel out, and we got a huge equation, which is nothing to do with reality. Such a reaction really doesn't happen that in one go, you cannot add up ammonium sulfate and sodium hydroxide with copper oxide, and you expect copper and nitrogen gas. No. This requires a different condition, this requires a different condition, so you have to do it in 2 steps. But for stoichiometric calculation, to establish a stoichiometric relationship between these species, we can outwit the question. Question is not demanding us to do it in one go, or you add those reaction equations which have no reality to take place, but we will do so in pen and paper. We cancel out and then write this huge equation. Then our interest is ammonium sulfate, copper and nitrogen, not to find how much of copper, how much of ammonia is produced. Ammonia is out from the picture. But in our program, in the previous discussion that we made, we first found the mass of ammonia and then used it. What's the fun of doing that? So only a little time will be required for cancelling to perform algebra. You might argue with me, the same time will be required to perform algebra as much as to find the mass of the product of the first reaction. I think that will require more time. This will require less time. You try for yourself. Then establish. So 1 mole gives 3 moles of copper, 1 mole of nitrogen. So 132 grams produce 3 into 63.5 grams and 22.4 liters. This is liters because it is asking in terms of volume. So 2.06 grams gives how much of copper, how many liters of nitrogen. So in one go, you can find out. And I have given some assignment, 15 assignments problems for this. We are concluding this part, but the next part we'll be doing, I'm showing you in part 2, limiting reactant concept we will be doing in vigorous ways. And also percentage of purity, we also do composition of a mixture, and of course. So that will be consuming 40 minutes more, 40 to 45 minutes more. The most time consuming part is over, right? So bye bye for now, and see you soon in my next video. Until that, you solve these 15 numericals pertaining to this, what we have discussed. Bye.